And what we talked about last time was our first model of computation. The trajectory of the course will take us through increasingly complicated models of computation that will facilitate more powerful machines and so will allow us to answer more complicated questions. And so we're starting at the beginning with the simplest kinds of questions that we can answer. And when we're thinking of a question that we can answer, what we really are thinking of is a pattern that we can detect. And so we're thinking about discriminating between strings over some finite alphabet and looking for those strings that have some pattern as opposed to those that don't. Now, these strings can encode all sorts of more complicated objects. For example, they can encode file names, or they can encode descriptions of other computer programs. But at the heart of the task that we have for ourselves is getting an input string and deciding whether it is or isn't a member of some set that we're trying to describe. So in order to get comfortable with this, we need the basic definitions. And we talked about them last class, but because they're so important, it's good to see them one more time. So remember all of the metaphors that we've got between these formal objects and language. So our basic set of symbols will be called our alphabet. Now, common alphabets that we might use are the binary alphabet. So our alphabet might be the set whose two elements are 0 and 1. Another common alphabet might be if we want to give ourselves some letters that we're comfortable with. But really, any finite collection, non-empty finite collection of objects can be used as an alphabet. Typically, for counting lengths and stuff, it's convenient that every character in the alphabet just has a single representation. We don't want multiple bits over here representing a single character in our alphabet. Okay, so each character has length 1. And then we can build up strings over the alphabet by looking at lists of symbols from our alphabet. Now, strings are always going to be these finite lists of symbols. And then if we take a collection of strings, any old collection of strings, that's a set of strings, and it determines a language. Okay? So languages don't need to have any specific property to give them to be a language. But what we mean by the word language is a set of strings over some specified alphabet. All right? Now, a regular expression is what we defined last time. And remember that we defined it inductively. So a regular expression is a piece of syntax that's built up. And the kinds of things that we can do to build up our regular expression is we could have characters from our alphabet. We could have the empty set symbol. We could have the epsilon symbol, which stands for the empty string. And then we could combine various regular expressions using the union symbol, the concatenation symbol, and the Kleene star symbol. Now, from that regular expression, that piece of syntax, we can then deduce the set of strings that are described by the regular expression. And so that's what I want to start off with.